company way back when. And it made me realize there's even a higher level of generalization that can be done where data is dictating system parameters instead of just fitting models. And so I'm eager to add that to my personal curriculum. That makes sense, Dennis? Sorry, I'm off camera. Oh, I get the bad lip read. Tom, you're just not smart enough to understand what I could teach you. Oh, go on ahead.
Yeah, fine, of course. You're the data scientist.
No, so I'm not just a data scientist. I'm also a multi-physics modeling engineer and control system designer.
Well, then you necessarily got it right.
Okay, good. Because really, your model was parametric, but it wasn't necessarily physics-based, correct?
Well, it's more complicated than that because it's inside the code. It moves around like a robot. It is very close. It's close to a Turing machine. So it does move around like in a labyrinth. It is physical.
So I have to explain to everyone what just happened. If you've watched the movie, The Imitation Game, there's this key scene where the other mathematicians are approaching Turing and they're wanting to know what he's doing. And he basically says, y'all probably couldn't understand it anyway. And I feel like we just had a repeat of that scene.
Yeah, that's correct. It's physical. A Turing machine is both abstract and physical.
That's good to know. I can see it occurred to me when I think about what that machine was able to do, and I'm coming on video again, and Dennis, there was a point in the movie where he's explaining we can't let the Germans get a hint that we broke their Enigma machine, because if we do, we have to completely reconfigure this machine. Or maybe it was the same machine would work, but they would have to find a new way to train it or something. Whereas they had that big breakthrough. It was kind of like
the main reason is that the Germans would have known that we knew, and they would change their strategies.
Okay. So it's
whereas
not
this way we could manipulate them. There was a lot of deception. We could create false things and see how they reacted.
So Dennis, we're at a unique day today. Amar, who is going to show up and talk about a PhD track in STEM or data science, regretfully couldn't show up. And everyone enjoyed your show where you invited your family the other day. Why don't we just continue talking about that? Geith, are you good with that?
Don't forget, I'm one of the German right now.
That's right. And then
we're talking about Germany 80 years ago. We're not talking about
yes, I understand. I even watched the movie, but I find it's good to say it right now. This is the only reason.
So
I was born in Germany, Geith. I was born in Berlin. I spent my childhood there. Yeah.
Well, there's some other advantages today. Mom's not here, so we can get away with anything. And then Kimberly's here, so she can referee for us. So I say we continue that talk. I had so many questions.
I think you should guide the talk. You should direct the talk. Just ask the questions.
I'll try. So what I'm trying to understand, Dennis, is in my limited mind right now, I think in multi-physics, in other words, the way I approach physics-based modeling is in a very unified, generalized approach. It's in other words, it's continuous. But then when I look at the data science realm, it's kind of like empirical modeling in the physics realm. So we can't always use first principles physics to model things. So sometimes we come up with empirical models. But I realized as you were talking the other day, what you did for that company was more akin to what Turing did with his Enigma breaker. And it's not really physics-based or data science, but it could be something like a little bit of both of them and still a little different. Now, I don't know if you're under confidence to not reveal exactly how you did it, but if whatever hints
the
you can give us.
confidentiality, the NDA is over. It stopped a couple of years ago, but I'm careful not to say too much. But Ugo asked the right question. He said, "What is it?" Now, the problem I have is that I looked at nature. I looked at nature. I looked at how cathedrals were built because they didn't have algebra. I looked at ants. I looked at honestly, it just came out of my mind, and it's extremely close to Turing. Extremely. It's just that Turing went from left to right, and I just added a multi-dimensional system. It's very difficult to say what it is. I couldn't tell you.
Yeah, and I see what you mean. In other words, how do you classify it? Well, I'm not sure.
That's why I say the closest I can find is Turing. But of course, I added neural stuff at some point. I added all kinds of things, but it's physical. It goes through a physical labyrinth of the supply chain, but it can go through I didn't even design it for supply chains. When I thought about it, I said, how does a human being think? That's where I started. I was sitting outside in my garden. I say, what does a human think? How can I do something universal so I don't have any maintenance to do? That was my problem, because I don't want to hire. So I was just thinking, any person will do an event. That event needs to be done somewhere with a main constraint and with constraints. And I don't know, I just built it and it looks like a Turing machine. It's extremely abstract. It's extremely abstract. When, in fact, at one point, people would pay me to get the source code and read it. And I said, sure, here, you don't even need to buy it. Look at it. No one understands it. It's abstract.
Okay, Dennis. I'm always, since it's abstract, I like to abstract the idea. Let's
maybe
name
you'll
it like
help
this.
me. Maybe you'll psychoanalysis.
Not like this. I'm just a data scientist, small one. So since you are talking, both of you, but I want to look at it from, let's say, different point of view.
Yeah.
At the end, any task, even anything happened in the nature, even whatever it was, even if it's iterative, if it's continues a lot of things, but at the end there is input, there is output. Even the human life, it's a start, it's finished.
Yes.
Now, okay, I will make it like this. Once the life is started, there is many options. Once he is started, that means once he get the birth, these options start to be limited somehow, because he born in for specific family, for specific father or mother, specific country, all of these things. So now we go from the universe to that small room where he's born. And let's go to the next step. There is once, for example, not directly the next step. Let's say once he is 5 or 4 or whatever, he has to go to school. All the options on that place are possible. But once he make a decision, he make one decision from all possibilities. At the end, we find that the human, anybody is, during his life, he is drawing his graph. Okay. Now, I'm
It
just
sounds
trying
like
to
Tom.
simplify it.
It's like Tom is killing someone in his room. You know, he's chopping someone apart.
Oh,
Yes,
looks-
I
sorry.
think that.
I was letting Ivy out of her crate is all.
Oh, okay.
Sorry
like
for
you're
the
killing
noise. I
someone.
should have put on mute.
No,
What-
it's very interesting.
Okay, what I think about, even when I studied the neural networks and the deep learning concept on the first time, I was looking at it, and this is somehow, it's right now, it's even, it can be, let's say, confirmed that it's opening a lot of options, and then task of training, it's to find the best combination for a specific task. This is the great why deep learning is working at the end, because you have a lot of input and then you are able to find it. Now, from these two ideas, I'm just trying to simplify what you did without going on depth, just as a concept. From these two ideas, always we are doing the same all
Yep.
time in our life, on systems, on computers, on space.
Yep.
We
that's right.
are limiting the options.
Yeah,
to
it's
the best
called
one.
constrained propagation.
Okay.
In,
Exactly.
in, it's constrained propagation. You propagate and you constrain. In French, it's propagation contrainte. It's you open the tree, and as that tree goes, you have to cut branches off. It's constrained propagation. What you're describing, and
This is what I want to reach. This point. Now, nothing more to add. I will keep it for you. Yes, exactly.
Yeah, I agree.
Well, it's the way you tend a vineyard, the way you just described. You're constantly pruning, but so it will propagate properly.
Yep. That's what he's described. Now, there's one thing that is interesting, maybe, is that in the early 1990s, I was developing in Prolog. It's logical programming where you have an inference engine, you make assertions, and then you receive data as assertions. And I started out with this compiler, and I did a lot of things with it. The thing is that it cost around 15, let's say today would cost about $20,000 a license per site. So that was way too expensive. So I was thinking, why don't I develop my own stuff in C++, and I don't have to pay anything to anyone. So it goes back to what Gayeth is saying. You're going through a tree, and in that tree, it's constrained by the assertions you put into it. So
honestly, I was describing something from Prolog because I study it, even if I didn't work on it.
So
yes,
you were
I was doing the same.
too.
Yes, exactly.
That's why we got to the same conclusion. It's constrained propagation.
So a question, I still get the sense that, I mean, it's not data science and it's not physics-based modeling, but it sounds like it's a balance between the two, but more toward the physical science realm, but in a very generalized sense, to where just like in a set of differential equations, the parameters, the weights in the equations are based on system parameters, things that describe system characteristics. And it sounds like you had a nonlinear system in the sense of the parameters weren't constant, but you were updating the parameters based on data.
Yeah, that's right.
Okay.
But you're right about the physical thing, because it's not like Prolog. In fact, I could observe physically the path it was taking, like a Turing, like in a labyrinth. I could show you something, but it might scare you. Let me show you something.
Before you show us,
let me get something.
Okay. So I will save the comment I wanted to share until we're not on recording. But yeah, okay, Dennis, go ahead.
I don't mind. No one will understand what I'm going to show anyway. So I've never found someone. Here is the inside of how it works.
Yes, that's so clear. Thank you.
Really, this is a real calculation.
That completely dismisses all my confusion now that I see that.
So
No.
people would ask me for the source code.
There is one
People would
thing
ask me for the source code, and they say, "How did it work?" I say, "I know. I can tell you by heart how to. Here's one calculation. All you have to do is understand that, and then you're okay."
Okay, Dennis, there is a point at the lower right corner. It wasn't clear on the screen, and this may corrupt our understanding. So please, you have to show it.
Yeah. What do you want?
Okay.
The lower right, he said.
Yeah.
Right there.
Or
that's where you saw the bug there, right?
Yes, exactly.
Okay,
and
Dennis.
That's my mind.
Uncle Dennis, I keep trying to picture what goes on in your mind.
Well, you just had it. That's exactly what's going on in my mind. But really, that's exactly in it. That is an exact portrait I drew. Yeah.
Yeah. How do you translate that into code?
But that is in code. All you have to do is have matrices.
Okay.
And it'll go through the matrices like in a video game.
Well, and Dennis, when I think about, okay, I've got a multi-physical system.
I'm glad I cleared the everything up for you in one image.
When I've got a multi-physical system and I've got these sets of differential equations for this multi-physical system, when I look at the way I'm going to solve that with the calculus, it comes down to a set of matrices. But the matrices you're talking about are describing this process flow worldwide of this distribution and profit for the manufacture, distribution, and sale of products. Now, yeah, given enough time, anyone with good generalized modeling skills, I'd say the way you studied, or I don't, oh boy. I'm open to being wrong about what I'm about to say, but I would think that my generalized physics-based modeling skills would have been more helpful to me trying to accomplish what you accomplished than my data science modeling skills.
Yes. So, okay, now you said some very important things there. First, in what I like about France's, the mathematicians that were there, there are two ways of thinking in terms of geometry and algebra. These are two ways of thinking. The great French mathematician Poincaré described it. Cathedrals were built with geometry, not with math. They were built with Roman numerals, so they didn't have math. Now, to understand it, it's not very complicated. Go back to 20,000 years ago. There's Tom, you, me, Gaius, Ugo, and we're sitting there and we have to go hunting, okay? In those days, the unknowns were incredible. So we had to walk 3 days in a direction. We calculated the last time we went there, it would take us 3 or 4 days. So we already know that we have that constraint. And then we know that we'll have to hunt at least 1 or 2, 3 days, and we're gonna have to carry all that stuff back. But we might have problems with people that want to eat now. It might be starving by the time. So we developed all of this 20,000 years ago. I didn't invent anything. And if you look at the physical path it takes without taking our modern society thinking, well, we moved along physically. We're not thinking, we moved to somewhere. So we went to Hong Kong. And then from Hong Kong, you can abstract it. We went to a place where we manufactured stuff. That's the hunting stuff. Then we had to come back to Hong Kong and all the way back to Europe. So these models exist and you can't change them. It's what Gaia says, you're stuck. You can't change it. If you have a symphony, well, then all these notes are going somewhere. They're in line, they're in sequences. So all I did was take generalized these things in a very, very physical way and represented them in matrices and ran thousands of lines of calculations with hundreds of parameters.
Here, just only one question. Why to generalize it? And maybe I have answer in my head, but I want to listen to you, and or also Tom or anybody. Why to generalize in a physical way? Why, let's say, use the physics to generalize this?
Because that is my secret. That is how I tore all my competition apart, because I was always going from physical to real. And they were often, like, for example, I remember my first project. I started my first big one in the textile industry was in June 1988. General manager calls me in and he says, I want you to optimize the fabric in my company. And I say, I don't know what you're talking about. I'm working for what is now Airbus, and I know a lot about ships and fighter jets, but I don't know anything about. He said, you'll adapt because I know you. So what I did is I went into the factory and I followed the path of the cloth, and I say, why don't I reproduce that in my matrices? So it goes from there to there, goes from there to there, goes from there to there. Okay, so it takes that much time, it goes to that distance. And I said, well, actually, everything's like that. If you play music, you go from one place to another. For me, it has to be physical. I'm a cathedral builder. It has to be, I have to see it move. So I can see it move through the matrices and I know where it's going. I'm in an abstract world where there are no letters. It's just, I'm optimizing a path. In fact, it's called Pathfinder. Okay. Inside my C++, it's called Finder. It's just finding a path. The path you described.
Yeah.
So Dennis.
Honestly, sorry, Tom.
Go, Guy. No, Guy, please.
No, because I was thinking about it between let's say the logic, just like logical programming, and the physics, just like this. Logically, without any physics, if we use Tom gun just to put a bullet on my head, okay, the possibility for me to die is 50%. It's not that much high without physics, or without. So this is why. That means the physics will help you to find the correct constraint, the correct exactly.
Yes.
So this is just what I want.
Yes,
I
exactly.
want to highlight.
Yes, because then in June I started the program. In September 1988, I'd finished that first program. In September 1998, one of the biggest editors of textile software in the world, called Lectra System, which exists today, is #1 today. Lectra, Lectra. They were the biggest. They're the biggest in the world today, and they were very big at that time. They hadn't succeeded. So they came directly to the company and they began insulting me. They say, well, how did you do that in 3 months? We've been working on it for years. And I said, you know, I'm not going to answer your question. I just think you're just in offices. You don't know what a factory is. You don't know. In fact, you don't know what you're talking about. You're good mathematicians, but you don't know anything about a factory. So some months passed, and then the general manager called me down to Bordeaux, in fact, Cestas, and he said, why don't you teach my engineers what you know? And they said, what am I just spent 3 months in the company. What do you want me to teach them? Teach them. So I explained the physical world. We live in a physical world. I'm sorry to disappoint a lot of people, but that's the way it is. So by representing it that way, I can always know exactly what's going on, even if I don't know the subject. So,
Kim, we're going to come to your question. I had my mental hand up before yours, and I was trying to wait on Guy, but Kim, we are coming. Dennis?
It's cybernetics. It's like cybernetics.
But it sounds like you're doing a form of dynamic, sorry for butchering these terms, dynamic kinematics.
Yeah, kinematics, that's right.
It's more kinematic in nature, because you keep talking about matrices. You probably had to use a hyperspace instead of, because yes, you're looking at the physical world, but I'm guessing that your matrices have more than 3 dimensions.
Well, I mean, physically in the C++ program, they don't, but in terms of dimensions, sure, you can go up to 50 dimensions for one calculation.
Okay. But it basically is kinematically and dynamically related. That's the closest area of mathematics that you were touching on to model these processes.
Yeah, that means let's take an ant. Let's take my cat. My cat goes to the window because I observed, I learned a lot from my cat in terms of neural networks and calculations. So my cat goes to, and you have animals too, so your cat goes to a window that you open, right? You've seen that many times. And then this cat, you open the cat goes, so that when you open the window, it doesn't go out. You say, I just opened the window for you. Why aren't you going out? The cat will just sit there because it's calculating. It's calculating all the parameters. It's a bit cool outside. It's a bit warmer inside. Maybe if I go out, I won't get back to my food. If I go outside, maybe another cat's going to bother me. I don't know. It's piling up an incredible amount of parameters that
my cats do the same.
yeah, but cats are built like that. They're very, very intelligent and very careful. And so they're building up a number of parameters before making a decision. So when a system like this, which is like kinetics, reaches, let's say we're in Tunisia, and the system goes from the factory and reaches the transport system, it's going to pile up parameters. Today is Monday, but maybe I shouldn't get in the ship today because my container isn't full. Maybe I should wait until Thursday. And my container, maybe I should leave now. It's just like, in fact, when I was speaking about human beings, it goes to any animal life too. Animals think like us. We're just a bit more complex. So we're just piling up dimensions, parameters, and you just pile up and pile up and pile up until we say, well, I'll do it or I won't do it. So then you have to weigh your decisions and then you decide to do something. I mean, it's cognitive sciences too, you know.
So I have more questions that I want to ask, but I want to give Kim a chance to ask hers. Thanks, Kimberly, dear.
Okay, so this is a question for you, Dennis, and it's first a clarification question and then a next step question. So the clarification question is, you guys are all getting down into the dirt and talking about all the details and talking about all the elements of the details. And if I wanted to look at it from the clouds and really understand what you're talking about here, it sounds like from your experience, what you have done is you have gone from, let's say you have acquired your own personal domain expertise. You've then modeled that domain expertise and then you optimized it. And in the
that's an excellent, that's one of the best descriptions I heard.
Thank you. Okay. And so then in terms
you really nailed it. I created my own world.
So then, but then in terms of how you're looking at that world, from what you've been saying, you have used observations of other patterns. Let's say it's your cats or your ants or whatever you're talking about. You've looked at those patterns and you've said, could I apply this pattern to this system? And if so, would that help to optimize it? Would that be fair?
That's the best explanation I've heard.
Okay, awesome. I just wanted to make sure I understood it.
And maybe I'd say 25 years.
Oh, thanks.
Because the other person was the general manager of that textile company I was talking about, Electra Systems, that still exists. And he said, Dennis, anytime we present something, you take it back into your domain, which you master. Yeah, that's it. I created my own world, my own domain. And then I go hunting for all kinds of things I find. I go I shop in the algorithm Walmart. And if I find patterns I like, I just added them into my domain, in my way of thinking and my way of viewing the world. Yeah, it's my own personal way. Yes. And in the early days, people would ask me, I'd say, just an auto portrait. I'm just drawing what's in my mind. What I showed earlier is in my mind. That's how I think.
So Dennis, if that's the case, if you were talking to, your everyday analyst who's trying to figure out information that's given to them, so you don't have the luxury of building up your own domain, you're trying to deal with all the things that exist in the domain already. Do you scrap the domain that exists and build your own anyway, or do you take what's there and try and work with it? What would be your advice in that situation?
I always, since I really worked hard to create this universal domain, which is that's an excellent explanation. Then I put the patterns in, but then I can fit any kind of industrial data in there, because there's about, I have 500 parameters of all sorts and 200 hyperparameters. So I can fit anything you want, customer orders, anything can go in there.
Yes, but this is according to that, it will fit in your world. That means
Yep.
I will simplify it somehow. That means you will be a doctor when it's needed, or the physician when it's needed, or your model, not you. Now, my question here, and it's really, I don't think there is a need to answer it. What will tell us that your world is the best? This is my question right now.
My world, I never said my world was the best. I would just go to, now you hit another subject that is exactly with Kimberly. So Kimberly got the best description I've heard in 25 years is, Dennis, you just created your own world and you go around finding patterns. And if you like it, put them into it. That is exactly the definition. And then you come along and you have the second part, which says, how do I know what it's worth? And this is the way I sold it. I would go to a company, exactly like I said on Thursday, and they say, in my opinion, you're spending 500 million euros. I could save you 25 million euros. And let me finish, sir. If I were in your shoes, I wouldn't believe me. I wouldn't believe, don't believe a word I'm telling you. Don't believe a word. But I can prove it. So what I'll do is I'll do the project for free until it's proven, and you will pay me with the financial gains of the project. But just remember that here's how much I'm asking. I'm asking for this much. So this much is going to pay for 6 projects when I get it. So after that, I can wait. So yeah, if you put Kimberly and you together, Kimberly, I'm in my own world. Who says it's good? Don't believe me. And one of the big competitions I won is for a logistic company, where I came and I said, did the other competitors suggest to build a prototype and see who earned you the most money? I say, no, then why don't you do it? And I don't care. The best one will win. So honestly, I won maybe 5 times out of 6.
Good enough.
Let me ask this.
So Kimberly, thank you. You really gave me the
Yes.
next answer I'm going to give to everybody.
Thank you,
I
Kimberly.
forgot about it. I forgot about that.
So Dennis, this model, it's helping this company.
Yep.
How? How is it helping them?
That's a good question. So the first, let me take one that a German Belgian company, the Bayer. So are you working at Bayer, by the way?
Not me, but they turned me down. But Guy that works there, he's better
Bayer.
than me.
So,
So they took him.
So at one point, Bayer owned ACFA. They owned ACFA in Belgium. They owned that company because all that was one big company before World War II. And they had problems. So they had problems. They were manufacturing film for cameras, and miles and miles and miles and miles of it. I mean, and you had to optimize the forms on it so that when you cut the films, you didn't waste it because there was silver in it. Okay. So let's say you have a lot of material, and if you don't optimize it when it's cut, you're going to lose a lot of money. Now, where I came in those days, if you saw the drawing, right? I showed you earlier. Okay. that's my mind. I can think in huge volumes. You can give me, I can run a calculation in my mind. So they came up with it. They said, we've been working on this for 5 years with IBM, with MIT, and we haven't found the solution. And I said, I can bring a prototype. I remember it was May 22nd, 1991. I said, I can come back in a week with a prototype. So they said, why would you believe me? I said, don't believe me. I mean, I'll just come back next week. I'll develop it. So I developed it. I came back a week after. And the guy said, would you be able to save 1% of all the raw material we spend in 1 year on all our sites in the world? And I said, sure, 1% seems very possible. And they said, you know how much money that represents? Yeah, fine. And I was with IBM, and IBM came and said, sure, we just want 1% of your 1%. Give us 1% of your 1%, and believe me, Dennis will be happy. In fact, it paid for my mortgage. I was very happy. So I presented my solution, and I told the company, do not believe me. You will pay me in 1 year. When 1 year after the production's over, we'll go to the financial department. I know you're very honest people. I have no doubt about it. I mean, we're talking to very organized people. And in 1 year, if I don't make it, well, you don't give me anything. But if I do, you give me 1% of the 1%. So that's how I helped the company. Of course, I got the 1% of the 1%. I shared it with IBM, but it was a lot of money.
But what I'm asking more specifically, you've got this model. It's predicting their process, I'm guessing.
Now, this time I was just optimizing. It was pretty complicated because I had to take sets of the customer orders and fit them with sets of the raw material, and then put them on machines, take all the constraints into account, including changing times and work times, and save 1% of the raw materials compared to what 5 people were doing by hand and trying to beat me every time. So so I was just doing better than they did.
But this model sounds different from that distribution model.
Yeah, this is the father of the distribution model.
Okay, but it still used matrices and kinematics?
Yeah, it was Prolog once again. Well,
okay.
In fact, I was closer to your domain because I was stuck at one point because I had solved the problem, but it was too slow. It had to run each plan had to run in 2 minutes on an 8286, if you remember those processors.
Yeah.
And I had millions of calculations to do in 2 minutes. So it wasn't going fast. So I had these problems I had to solve. So this time, I admit I had to go out of my domain to go hunting for and I went into Boltzmann, and I went into Henri Poincaré, and I applied gas, the Boltzmann equation. I was looking into the Boltzmann equations in Henri Poincaré, and I solved it that way. So I was doing a lot of stochastic calculations early in the pipeline, and then it went back into constrained propagation. It was very complex. It's my most complex project. And then after that, how could I help a company in the supply chain? Well, that's easy. For example, one for warehouses. Let's take a warehouse. Okay, there's one project where I did everything in that one. Is where do you build the warehouse? Where? Where? In the field? In which city? Next to which road? Where do you put it? Where are you going to put that warehouse? So that's a huge problem because you can save millions of euros if you put it in the right place and lose millions of euros in another place. So that was one of my big projects in 2004, 2005. And this time I used part of what my universal model, and then I used other calculations that I took from astronomy. So it goes back to what Kimberly says, I have my own world. So I was thinking, where is the best place, so I was using astronomy calculations. And so how would it help the company? It's pretty easy. On the first calculation, I came in and they say, well, Dennis, you just saved €1.5 million on one calculation for maybe 1 or 2 months. You know how much that represents in 1 year? And I said, yeah, that's fine. He said, but the problem is we built the warehouse before we met you. So I said, next time you're going to decide where the warehouse is. So that I did that calculation for them, and I proved that I was earning billions. And they said, now that you found the place, build us the warehouse. Now run your little agent, because there was one guy that really understood what it was doing physically. Said, run that little agent, but physically in my warehouse, and optimize all the trajectories in that warehouse, because no one in my company can do it. I have 300 engineers. Not one can do what you're talking about. So do that. Okay, of course, you have to be in that little drawing I showed you to do it. So I optimized it, and they built that warehouse exactly the way I suggested. And then a funny thing was, maybe a few months before I sold my company, the manager called me back. He said, okay, you found the place to build the warehouse. You set the configuration for the warehouse, but now we need you again to organize all the entrance and all the flows in real time. When the truck comes along, what do we put in it? Which truck do we take? How do we do it? Which person goes and get it? Do we use it? And I said, listen, I'm over 60 now. You think I'm selling my company. You think I want to work? He said, what's wrong with you calling this? I'm old now. Why are you calling me? What about your 300 engineers? Can't you ask something? You have engineers from Ukraine all the way to all over Europe. He says, and that's going back to Kimberly. He says, you're creative. You have your own way of thinking. And we've noticed that your own way of thinking earns us money. So I started this project, and I scared them to hell, because I did it for a few months. Then I got there in the morning at 8:30 in the morning. I said, we're going to scratch everything that's done up to now. And I want to talk to the people physically, what they do. It goes back to what I'm always saying. I want to see them work. And then I just reproduced it in my model. That's all, in my domain. So Kimberly has the key. I have my own world.
But Dennis, once you have that model that's created,
yeah.
How are you using it to optimize? Is it now they can explore options using the model? Or are you using the model to find the optimal?
Now you're getting to a more complex thing where I'm an advocate of spontaneous order. I think the chaos theory. I think we live in a world of chaos. So this is when you call me the philosopher. I've worked in so many companies that I've noticed that everything is chaos. And that when people give me data, it's always wrong. And if you clean it all up, it's wrong the next day. Because if you're doing a set of operations, it depends on the person that's doing on the machine. So we're living in a world of chaos. So any theory that someone's going to give you on scheduling or planning is wrong, because it'll only be good for one day. You have Joe Biden that comes along and he says, I'm going to do a $3 trillion plan. And believe me, our country needs infrastructure. He has this idea. It's his idea. Let's say it's his domain. He says, if I do it, everything's going to be better in the United States. And at first, people don't know how to react. But then after, it goes where it's going now. Nothing goes as planned. So if you take chaos, and then the other side, you say, I'm going to build a system that's so precise and so fantastic, you'll see, you just follow it. Real life will tear it apart. I mean, it'll be destroyed. Your software will be destroyed. Everything will be destroyed if it can't take chaos. So I believe in spontaneous order. I believe that all these people that are doing these things fix things because no one wants things to go wrong. So they're always doing things in their factory to get on time. So tracking is a very important factor of my calculations, real-time tracking to know what's going on if I can get the tracking. And that will reorientate the whole system all the time. And you have all these people and all these systems. In fact, they're creating their own, it's their own world. It's a portrait of their own world.
So your model is tracking the chaos.
Yes, and it's representing the chaos, and every time it's trying to give it the best direction after that.
Okay, there's the key right there. How is the model giving the best direction based on the current chaos?
Well, let's say you have Tom, Kimberly, me, Gayeth, and Ugo, and we have to develop something. Let's say SQL, or let's say Prolog. Let's take Prolog. Who's going to be best in Prolog? Gayeth. Gayeth will be the best person with Prolog. Who will be the best person maybe in SQL? But maybe you will be. Who will be the best in something else? So maybe it'd be Kimberly or Hugo or me. What I'm meaning is in a group, no one has the same efficiency. It doesn't exist. You can't plan something with equal efficiency. So I have to select now who I'm going to take for Prolog. So suppose I say Gayeth. Gayeth, you're the guy for this week. You're going to be doing Prolog all week. Oops. Gayeth is also the only person that knew C++. And that means that no C++ is going to go on this week. Uh-oh, maybe I shouldn't take Gayeth. Maybe I should take a little guy that's not as good as Gayeth. Let's take Dennis. He's not as good as Gayeth, but he can do Prolog. And Gayeth can do C++ and Prolog. So I'll have Gayeth do some Prolog and C++. And so you can't just choose the best all the time. The best is the guarantee of failure. If you're always taking the best machine, the best person. So that's where I have intelligence in the system, where I have parameters balancing all that all the time, saying, no, I'm not going to take the best one all the time. If this person's, so there's a load balancing system inside which will choose the load and the competence. So that the system, sure, I mean, interrupt me, you'll never talk.
It's very hard to interrupt. Okay.
Just say, Dennis, shut up, I want to talk.
Okay, so from what you've been saying, again, I've been following what you've been saying, and it sounds like what Tom was getting at and what you are just addressing now is this idea that when you are figuring out how to optimize and how to deal with the chaos of reality and the chaos of how systems change, you are looking at equations and using those equations and how they work as your weights for the parameters. And if that's the case, how are you categorizing and looking at equations? And when you look at an equation, when you break down that equation to try and figure out, let's say, for example, what you're going to use for spontaneous order, are you looking at the structure of the equation in terms of the factors that go into it, the variables that go into it? Or are you looking at it in terms of the relationship of the variables to each other and which ones drive it?
You could be a consultant on my system. I mean, you nail it every time. So yeah, I have an equation and I'm looking at all the variables that can influence it. Like suppose I take a machine. So we had this example. I said, in the end, we're not going to choose Gayeth all the time because he knows so many things we need. But I have to calculate if there's going to be interruptions. Is he going to be interrupted? If I asked him to work 5 days, did he plan something else during the week where I'm going to have to go Monday, Tuesday, stop on Wednesday, and then go on Thursday? So then I introduce a distance calculation where I say, if he's interrupted too much, this can't work. Then I say, well, if Gayeth maybe is the best, but Dennis has been working on it since last week, so he might be finished on Tuesday, but if we put Gayeth on it now, he'll be finished on Friday. So how does that go with the next process that's going to happen after? Because we have to see what's going on after. So suppose that Gayeth is the fastest person to do something, but then the guy that's going to do the interface for the customer is the slowest guy in the company. So now I have a machine that's going full speed and it's piling up stuff for the next person or machine that's so slow that it's useless. Why did I take Gaiath? That was a big mistake. I'm going to take the slowest guy around because I want to fit it in with the slowest guy that's going to follow so that I have some sort of logic. Otherwise, I'll just be piling up stuff, like let's take a sewing machine. A woman is sewing and she's sewing so fast that she piles up stuff that goes too fast for the person people are doing the packaging after. They say, stop sewing so fast. We can't package what you're doing. So then I would just take her off the assembly line and say, hey, you're too fast. I'm going to put someone much slower.
Dennis, sorry to interrupt you there. When you with the sewing machine example, that's the where you start coming into the 5S and the push and pull concept along the process flow, right? If you push, you push too much and then the person can't keep up. So you introduce the pull process on each stage to keep the work in a good, steady flow throughout.
Yeah, that's right. But I have more parameters, like Kimberly really nailed it. There are more to that. What if I have someone that's going too slow? So we're piling up parameters now. Person's going too slow sewing. So now I'm piling up stock. I have too many buttons in my too many buttons stored up. What if I'm sewing, but then after there's no machine to wash the jeans? And then what if I'm doing all this fine, but there's no truck to transport the goods until next Thursday? What if I'm doing very well, but there's no profitability on what I'm doing? I'm just piling up work that wasn't ordered by customers, which means I'm just wasting my time. So in the end, Kimberly, I can end up with maybe 50 parameters to make that decision.
And are those parameters predefined in a database that you have of different equations and their relationships to each other? Do they get pulled when the situation arises that calls for them?
Now that's the interesting part, is the system just reacts to that like a cat and says, no. It's because each parameter can be soft or hard. Each parameter can say, because if everything's hard, you get no schedule at all, because no one has everything at the same time. So each parameter can be constrained, hard constraint or soft constraint. We say hard, I won't do it. Soft, I'll do it anyway. And it can also have a tolerance parameter, say, well, if I only have 80 buttons and I had to add 100, I'll go for it anyway. So it in fact, it goes on by its own. It's not fixed that much. It's not, these equations are just piled up, and the system.
Are they piled up in a stack format? Are they piled up in
stack? They're stacked. No, there's a data set where you have to enter your parameters in the right columns and fields and all that. Okay, but once it's running, they're stacked.
And what determines where they get pulled from the stack? The efficiency, or you know what I'm saying? Like what determines where it gets pulled?
Everything I just said. It has to go through this test where it answers everything I asked for.
Okay, so you're defining all the criteria, and with part of that, you're leaving soft and hard constraints within that criteria so that it has the flexibility to adjust if one situation doesn't exist first, then it goes to another.
And the quantities don't have to be exactly the quantities. It can. So it's what I do is it's called the plan of the plan. The person has to decide how it's going to be. Now you can understand that the real problem is when all these parameters and data are stacked up, how do you know what it's going to do and how it worked? And how can you do something like that? And the only way to do it, that's why we're not too much of this, is to have everything in your mind. You can't do it physically. To create this kind of program, or if you're working for a customer, you have to have everything in your mind. You have to run it in your mind. I had a few competitors I met, and they would lie down on their couch and they would run the whole thing in their mind and just pop up after. We're schizophrenic, we're autists. I'm just one guy that knows, I'm just one of them that escaped and knows how to talk, that's all.
Forgive my question on down and dirty details. I'm getting into the math now. You've got this chain of kinematic related matrices, but again, the dimensions aren't necessarily physical space. They're just space that describes the space of the problem.
Right.
And so I understand you to say, oh, Guy couldn't show up today for this role, Hugo showed up. So at that point in the kinematic chain of matrices, I replaced the Guy matrix with the Hugo matrix.
Yeah. But maybe the Hugo matrix works for one parameter, but it won't work for the constraints. Let's suppose Geith was one factory and Hugo's another factory, and then the other constraints will change. So it's always bouncing around like a flipper thing.
Right. So the model has both the ability to say, okay, you can make that decision, but this will be the output. But the optimal operator matrix at this point in the chain would be this person for the given state of the current chain.
That's right. There's never one optimal person. It's always in context.
So I'm getting a handle now. You've basically generalized kinematic modeling to any spatial problem at all. But what the model can say is, now I'm going to look at options and I'm going to find the best set of options. What I'm wondering,
I wouldn't use the word best.
No, let me.
One that works.
Okay. Yeah. In other words, this is so complex. I'm guessing, based on the way you just responded, no, Tom, this is so complex that I can't really find the maximum or the optimal. What I can do is say, oh, at this point in the chain, this is the best option.
Yes, but there is one constraint. There are KPIs, and that's if something will be late or not late in the supply chain. Sometimes the customer will say it's 0 late. SAP, our ERP sent you a delivery date. That delivery date must be respected. That's it. There's not one day, you can't be 1 day late. So I don't care what your system does. I don't care how you built it. I don't care where you come from. I don't know what it is, or I don't even care. I just want my orders to be on time. So do anything you want. And but I want my orders to be on time. That could be one constraint.
I see. So but basically it's an alerter. It says, oh, you just made this change. That's going to affect this KPI. Here are some options that will keep that KPI healthy.
Yeah, we'll tell them why. You're missing raw materials. You don't have enough. Yeah, bye-bye, Kimberly, and thanks for your psychological approach.
Is that what you're going to call it?
Yeah, you're my doctor now.
You're the intellectual referee today, Kimberly.
Okay.
Well, I forgot about what you said. Now I remember it. It's my domain. That's right.
All right. Well, enjoy that. Have a nice weekend, everyone. Bye-bye.
Yeah, have a nice
Kimberly.
weekend.
But to Kimberly's points, this world you created still has to align with reality.
Yeah, of course.
Yeah.
Otherwise, I wouldn't be sitting here. I wouldn't be able to afford a smartphone.
So this is very helpful. This is very much like Lean Six Sigma, but on the extreme mathematical method of helping with lean. In other words, Kanban and black belt type work and all of the quality engineering and manufacturing engineering optimization stuff. But let's not get constrained by that. You could generalize that, as we've seen the books, the Unicorn Project and the Phoenix Project. They basically copied what happened in the famous book, The Goal. And really,
yeah, the goal, of course, the goal is very
the,
important book.
Yeah, the goal is the closest thing I've read to the way you're talking right now.
Yeah, of course. Goldratt really, yeah, Goldratt was something that comforted. Now, let me tell you something, since we know each other. What I developed is what Kimberly said. It's my mindset, and it started when I was 7. It's not something I read in books after Sigma and all that. It's when I was 7 years old I began thinking like that. That's all. That's the way I was thinking. I was thinking in paths and patterns, and everywhere I would see. And I looked that up. It's called the mathematical eye. It's just you have people like that just walk around, and it's the mathematical eye. Just translate everything into forms and matrices and distances. That's just the way my mind thinks. And then as theory, I learned theory, as Kimberly said. I just picked up interesting things that I just added to it. So it's just a grown-up child.
But this is interesting. The data that was fed to your model was basically like changing gears. Oh,
yeah, but it's still working. It's not
no,
it is. It's still
no,
running.
Forgive me. Yes. What I mean is
that is fed to the model, although it's not mine anymore.
It's in other words, now I'm getting the feel for the type of data you feed to your model. It's not a type of data that can easily be dirty. I mean, if you give it a wrong parameter, it's just going to be a little off in its estimates. For example, I love your illustration of, oh, Geith was on shift, but now with these particular gears that are in the chain, or these particular kinematic matrices that are in this chain or this fork of the model, if you replace Geith with Hugo at this point, that's going to have this effect on this KPI.
Yeah, that's right. That's right. That's right. You're ready to use it. And then, so what happens is,
I got to tell you this, Dennis, I don't want to be ready to use it. I want to be ready to recreate it for a new situation. That's why I'm asking the kind of questions I'm asking. How can I use my mathematical knowledge to create a new model for a new domain the way you've done for these other domains?
That's something you'd have to ask Kimberly. Because she's right. She's reminding of where it's just the way I think. It's not something I invented. It's the way I think. I think like that, and I've been thinking like that since maybe age 7. Age 7 maybe is the time where you rationalize. It's just the way I think. And after, of course, I learned a lot of things that I added, just like Kimberly described. But I don't know. It's like it's who I am. It's not
your emphasis on the intersection. Forgive me if I don't say this just right. That your emphasis on the intersection of algebra and geometry, basically more geometrical, more kinematic, even the not just kinematic, but dynamics of I know kinematics covers dynamics too, but it's basically multidimensional calculus. We could even say that. It's a spirit of, oh, what I learned to do was abstract kinematics beyond the pure physical realm and map kinematics to processes that I see on a floor.
Okay, let me give you an example, because after it's going to be...
Was that accurate? Was that accurate, or am I off?
Of course it's accurate. I mean...
Oh, thank you. I just needed confirmation.
I know who I'm talking to. I mean...
Okay.
There's a way, because after it's going to be soup time. So...
yeah, it's coming up.
Yeah, it's coming up. So let me give you an example. Let's take you can do a mind experiment. You can take a map, of the United States, because it's a beautiful map. I mean, looking at the map of the United States for me is looking at a masterpiece. I mean, okay, so if you look at a map, these wall maps we have there. We have one here in our house. Look at the wall map of the United States. I mean, you can dream. You can dream for hours looking at it. I mean, you have the West Arizona, the history of the United States, Texas, the Spanish period. Okay, now you take that map, and now you're just thinking that you're an AI, you're an agent, and you're driving all around. You're driving all around that map all the time. In fact, you've driven everywhere. You've driven everywhere. And I used to drive cars. I think I already told you that I would deliver cars with AAA over there. And you're using your intelligence. If I drive too long, I won't find a hotel. I'll have to drive in the car. If I stop, I'll eat maybe an hour, but maybe it'll cost too much at that place. I'll go to a fast food over there. Okay, then. So you have all these constraints, and I have to be careful with gas because otherwise I'm going to miss the gas station. If you take everything in that model, then try to fit another model into it. Fit a model, any model you want. Take anything you want, healthcare, anything. And if you can fit it in there, you can do anything you want.
Exactly, Dennis. That sense, according to that, we are talking about warnings, alerts, constraints, and action.
Yeah.
And relation between all of that. That's all. This is what how we can summarize it. Life.
Yes, life. So yeah. So if you take that, you can't invent things that don't exist. You know that it's what you said. At one point, you only have these choices. If I'm out of gas, I'm going to have to stop to get gas, or my car won't go forward anymore. So if I didn't plan before, it won't work. So if you take a map, the map of Europe, you can take the map of Europe, Gayeth, which is a beautiful map too. I just love to look at maps. And then you look at all these maps, and then you can figure out how you would drive. And if you can put any situation in that map, well, then you have the mathematical mind of thinking algorithms. But you just have to remember the main rule: the map is not the territory. At one point, you're going to hit reality. Because the map will not be the territory. The territory is going to guide you after. There might be a roadblock. There might be an accident. It might be raining. So you have to take the territory and feed it in through tracking. So Tom, if you want to do it, take a map and do it. Write it down. Write everything down on another topic on a map. Say something as abstract. I'm going from Tucson to Amarillo. Okay, I'm in Tucson, Arizona. I'm going to Amarillo. What can happen on that road? Okay, now how can I transpose it into another subject? Education, music.
So I want to make sure I've characterized accurately what you've done. I think I get it now.
I don't think I did anything. I just did what Gayeth did. I reproduced life.
You and I are old enough to remember the days of adjusting our TV antenna to get a better signal.
Yeah, of course.
and tweaking, wanting to have a finer adjustment to the radio dial. Okay. Yeah. What I understand is your models, by Kaishan, your models, you would give them to the company, and they would, it's like what Turing did. They would enter those settings for the day from the message, and the machine would spit out the results. So you were basically saying, these things have changed in the data that's easy to not get dirty data on. It's not hard data. It's just some data about the changes in parameters of the system. And when you do that, here's the signal output you're going to get.
Yeah, that's right.
Now, that's brilliant.
It's a map. I just created a map, my map of my world, like Kimberly said, and people just have to drive in my world. That's all.
Now, I'm not taking anything away from you as I say this. It told them what would happen if they made those dial changes, but it didn't tell them. And again, I'm not taking anything away from the brilliance of it.
They can't make just one thing. They can't make dial changes. This goes back to what I said Thursday. No. They don't make dial changes. I give them a system. They have scenario 1, 2, 3, and that's it. And their data does the rest. Yeah, their data does the rest.
What I mean is,
but there are some dials.
Their dial changes are, Hugo shift is over, Guy shift is started.
Yeah.
That's what I mean by that. That, in other words, they're not touching your model, they're touching their system. Your model tells them, oh, with the touches you just made to your system, these are going to be the new KPIs.
But yeah, you're there, but it goes back to my basic philosophy before I go to the philosophy of my soup, is which is about the most important philosophy that I have, is never miss a dinner with family, is I believe in spontaneous order, and I really believe in it. I'll give you my example. Look at the world. Okay, so in the world you have governments that make plans and everything, and somebody up there laughs all the time because I've never heard a politician do what he says, or a government. Okay, it doesn't. So what happens is spontaneous order. It comes from the bottom, it goes to the top, and it balances the world. I believe that for everything we do, there's an opposite. Everything that we do good, there's something that does it bad. But that's my core belief. There's always a good for a bad, but it's always a bit better than bad, which means that's why we're 7 billion people and not 5. Because if we were bad, there'd only be 5 people left on Earth. So maybe we're bad with climate change, we're bad about a lot, but we're 7 billion people, and 7 billion people living better than 100 years ago. So I believe in spontaneous order. I believe in people, I believe in systems, and I believe in workers. So I know that when I get the system rolling, the people at the bottom see the tracking, and they can compensate. They'll say, hey, Joe, can you work 20 minutes later this evening because I can see by the system that we're going to run late. John or Fatima in Tunisia, could you just call that guy and ask him to bring some raw material over tomorrow morning? So actually the people optimize the system. We're giving them a world, my map. They put their data in it. There are some optimizing algorithms in it, but it's the people, it's the democratic system, because you can't give orders from top to bottom in a huge supply chain. People do it right. A captain's on the ship. He knows there's been a storm. He says, guys, we're going to have to work a little more. We're going to have to get things done to get that ship there on time. So I believe in human beings that are just a tiny bit better than they are worse in any situation. That's why we're 7 billion people. I can prove it, and not 5, because if we were bad, the ship would have continued to sink all the time.
So, but I have a simple question. As your models would basically be aware of what they were doing and tell them the results, but your models weren't informing them that now, if you made these changes, you would get these results. It was only letting them.
No. I give them my first scenario is to do the best solution.
Okay. How did you find that best solution?
And then they can tear it apart if they want.
How did you find that best solution?
Those are the equations Kimberly was talking about. It is a constrained system where each time I take the best path.
How are you determining the best path? Is what I'm asking.
Well, you have several parameters. Do you want to have equal? Do you want to balance the load? Let's take a factory. You want to balance the load of all the machines. You want to use some machines first and the others after because you can't pay all these people. Do you want to make sure you get raw material on time? You go back to Goldratt. You choose one main constraint and then maybe a secondary one, and then you really optimize that one.
So it's a parameter search. It's a parameter. You're sweeping one parameter, searching how to optimize it, sweeping the next one.
I just have one, as you said, I just have one dial to turn and it's done.
Okay. I'm struggling there. I'm struggling. I know you need to go to soup, but I'm struggling there because the output.
The way you'll find it is do that map experiment with the Map United States. It seems easy, but it's extremely difficult. Take it and apply it to your domain. and you'll see things will go all by themselves. I'm on the road. There's no more gas. Okay, guys, that means that before starting on this road, you go into Death Valley. Have you been to Death Valley?
I know what you're talking about. Similar places.
Go to Death Valley without water. Okay, everyone that goes into Death Valley for one day knows that you have to take gallons of water in your trunk, or you're not going to make it through the day if your car stops. You have like a 2-hour, 3-hour window. So all I do is I take all this logic and I say, there's no way. It goes back to what Gaius says. You can't do anything. If I go to Death Valley, I need water. If I do this, I need that. If I have, but it would take more time, my friend. But you can reach the same level with a map or watch your cat.
This is why you've been emphasizing the knowledge graphs lately, to help people get there.
Of course. The knowledge graph is the only way to get there. Because that's the knowledge graph is what's embedded in us. We're born, it's hardwired. We're hardwired to optimize physical paths in jungles, in forests, to go hunting, to go gathering. We're physical. We're physical humans, and we keep forgetting about it. We're not abstract beings. We're physical. That's where we excel in physical itineraries and paths. And so if you build from there, you can build a solid system. So now it's time. Ugo gave me another name, Superman.
Yeah.
Super, and then 2 words. Superman. So Superman is going to fly off into his soup.
That's good. Good timing.
Okay.
Yeah.
So
tell Catherine we said thank you.
Yeah, I heard her walking around. But then she didn't come up and say, "What are you doing?" So I'm going to go down. It's very important.
Uncle Dennis, have you ever thought about taking maths as a lecturer in a university or a proper setting?
I taught. I was one of the first teachers of computer science at the Sorbonne University. And of course, they offered me to become an assistant professor and a professor, but honestly, they don't pay much here. So I do like to. You remember, I'm a primitive hunter, so I do like to get the meat, and the vegetables in the house. They weren't paying enough, and I don't like frameworks. Go back to Kimberly. I created my own world. I don't want to enter someone else's world.
All right.
The closest to what I could do is to be a Paleolithic hunter. That would really get up at 5 a.m. at sunrise and run for hours. Yeah.
Hugo's son, he stopped being an elephant hunter because he wanted to be lazier than that. He used his intellect to create elephant traps. That way he could eat all he wanted.
Well, now we can't hunt. We don't hunt. I was more speaking about food we could eat. I wouldn't kill an elephant.
I meant that.
But in the Ice Age, in the Ice Age, I would kill an elephant because that's enough meat for 1 or 2 months.
Yeah. No, I was just using it analogously, not legally.
Okay, so everyone, thanks a lot.
Thank you.
Now Superman is going to go to soup time.
All right.
And next time we'll listen to Amar.
Right.
Yes.
As soon as possible.
Okay. Bye-bye, my friends.
Goodbye, Dennis.
Bye-bye.
I'm still not sure. I get a sense of how he builds these models, but I don't get a sense of how he optimizes them.
I think the first thing I'm going to try to do is to wrap my head around Turing. Since the first day you said that, I have been trying to just wrap my head around it, just try to understand.
I think there is, guys, I think there is another lesson we have to take it here. And I think even Dennis was talking about the same. We have to find our world, not his world. And that way we can build something. How to explain it? How to explain it in a correct way? Always when you are thinking about, let's take the example that he mentioned. At the end, the life, it's like this. Whatever it was, the graph theory, for example, whatever it was your problem, you can simulate it as a graph with a specific way to calculate the weights for that graph, and if it's directed or non-directed or whatever, then you can find a solution. You can browse or parse or find a way to go from one point to another point in the graph. Okay, how to implement this, how to optimize it. Now here the customized work from his side. At the end, he goes to the problem itself and get the customization from the people who is performing that. I'm just simplifying. Okay, now let's go to the other part of it. Once the graph is not working for you, it's when you have collaborative tasks to be performed with the same target. Here you are thinking about different graphs for each agent. Okay, and at that point you will end up without optimal solution. You cannot find the optimal solution. One of the solution might be the optimal, but even you don't know. At the end, you need a solution. Once it works, it's okay. It's better than nothing. So I'm just trying to simplify it. Why? Because at the end, each one in our life, even if they are not, let's go again. Why the accounting systems or accounting methods are working? Because it's a word and somebody is adapting himself to use that word because it's beneficial. What's my point here? It's at the end, we have, since we are 7 billion, or right now it's more, we have 7 billion way of thinking. It can be clustered, it can be in different method, but at the end we have 7 billion unique way of thinking. With this 7 billion unique way of thinking, I think we will have 7 billion world at the end. And each one, it's doing better than totally randomized options. Because the most important is just avoid cyclic or circular references. Once you avoid that part, then you will reach your target. Whatever it was the problem, whatever it was the target. Define the target, understand the obstacles and the alerts, and avoid circles. Go ahead, you will reach. Limited options always.
I totally agree with everything you just said, Guy. What I couldn't pin Dennis down on is, okay, I can imagine how I could model this system, but I could not wrap my head around, is he doing some closed form optimization, or is it some type of, I don't think he's doing that, but he had some way to tell him what the optimal parameters were. And I wasn't capturing that, how he did it. Maybe he did it while he created the model.
Tom, it's not final. That means it's not for all the parameters. It's only for a specific stage he can get the optimal. Or a set of steps. And at that point, it will be very limited problem and it can be solved. Even technically, we have solutions for that. And then you will simulate it at the end.
And like he was emphasizing, hey, I have constraints. It was constrained optimization. So maybe and once he saw the constraints, he said, now I only have these variables. Now we'll optimize with these few variables based on the constraints I have.
Exactly. Once I optimize it, I have to understand the relation between these variables also, because once we lose a value from one variable, maybe other value, it will be higher, just like the time and speed somehow.
And since I was an undergrad, I've been sold on generalized modeling. In other words, hey, yeah, you learn differential equations, but don't think you can't apply them to things outside the physical realm. And then make sure you know how to relate the modeling methods across the physical realms to one another. Okay, great. Now, how do I take that into a business realm? How do I take it into a factory realm? And that's what I was trying to, because I've seen other approaches, but this more of a kinematic approach, it was, oh, that's beautiful. No, it's kind of like robotics, but it's abstracted robotics when you get down to it.
Yes. But I have a concern now. Maybe will change that topic. We will talk about something else. But the physical realm itself, it's even wider than we can expect. I'm not let's say I'm not this expert on physics. It's not my domain at the end. But yes, sometimes I'm reading something, I found it very, very, very interesting, very excited. Maybe because I didn't understand it, and I like magic, so maybe this is the reason.
My guess.
But honestly, what to do if you face in real business life a scenario just like Schrödinger cat, for example? What you are going to do at that point?
Yeah.
What I want to say, it's about the intuition. There is always something. It's over the. There is no parameter can decide it. Why I will give you an example. Why, since I'm smoker right now and the temperature is close to 0, why I will decide today to go to the balcony and spend 10 minutes smoking? Because I will enjoy this freezing weather. And I like it, but there's no parameter can tell you why.
Yeah.
So, and physics showing that it's not only how the human are thinking. There is something similar in the physics.
I can imagine how you know, this relates back to when we were still friends with Marchand, and we could talk to him. And you know, you hosted that panel, and Marchand and I agreed that, yeah, you could probably use reinforced learning to help you solve fuzzy logic systems.
Yep.
But now I'm looking at Dennis's thing, and it seems like if I put a constrained model as the world for a reinforced learning agent, the reinforced learning, and maybe Dennis is doing a form of reinforced learning and he doesn't realize it. I could imagine he's just doing one-arm bandit level optimization of his constrained model. It's quite possible that's what he's doing. Bye, Valerie.
Goodbye, Valerie.
Hey, Valerie.
See you tomorrow, Hugo.
Yeah, I'll see you tomorrow.
But you know what, Hugo? I never forgot. I kept thinking, wait a minute. And Dennis is right. Geometry is not math. We kind of think of it as math, but it's really not quantities. It's different. And kinematics is an area that blends geometry and dynamics. But as soon as you say that, what's beautiful is that mathematicians challenge us to think beyond what we can see and into realms of hyperspace that we can't imagine, but we can make real by the fact that we've posed a question that involves quantification. And ideally, you're still ultimately trying to answer quantification questions with geometry and kinematics too. So what I don't want to happen, I don't want to be constrained tomorrow by the math I know today. I don't want, it's important